Good morning, good morning, good morning, and how is everybody doing today? All right, so today we are moving on from postulates to common notions, which you should see up one of these directions. Okay, anyway, here we go, and let's get started. The first thing I want to say is the difference between the postulates and the common notions, because those can seem like very similar things. The reason they seem like similar things is because they are similar things. However, there are some differences. There's one difference. Basically, with the postulates, Euclid was giving you the things that he wanted you to accept. He's like, I'm not going to try to prove it. You need to accept it for all this to work. So just kind of work with me here, go with me. As long as all that's true, then the rest should work. With the common notions, the same thing is true. Like, you have to accept that these things are true for all of Euclid to work, what's coming after all this. But with the postulates, he's asking you to believe it. With the common notions, he basically thinks you do. What he's saying here are 5 things, and it's only 5 common notions, but here are 5 things that basically I'm pretty sure we all agree on anyway. That said, let's go ahead and state it. And the reason for stating it is that when you're doing something highly logical, like math, or sometimes philosophy, geometry certainly, when you make a statement, you want to be able to go back and prove it. Say, look, this statement follows from these other things that we've already agreed on. And what Euclid is getting ready to do is he's going to start trying to prove some pretty cool stuff. And he's going to prove it using the definitions, the postulates, and the common notions. So even though he thinks the common notions are things that everybody agrees on, he wants to write them out. He wants us to think about them for a few seconds. He wants them to be able to be there, kind of recorded, so that when he starts doing his proofs, we can look back and be like, oh, yeah. This has to be true because of the common notions, as well as because of the postulates and of the definitions. All right, so let's go ahead and let's do the common notions. All right, so common notion 1. We're going to keep, like we did with the postulates, I'm just going to start centering the numbers here because it's sort of a full notion. Common notion 1 is, apparently my PC is not protected. It is actually. Common notion 1 is that things which are equal to the same thing are also equal to one another. And demonstrating with this is actually one of the places that our little PowerPoint scheme here is going to come in particularly handy. Our use of PowerPoint is going to turn out to be really useful. So let's go ahead and let's talk about triangles, because I like triangles, and so does Euclid. Okay, and since I like my triangles green, we're going to keep it green, and of course we don't believe in outlines here in geometry, so let's go ahead and get rid of the outline. All right, so here's a green triangle, right? Okay, that's a green triangle. Let's call it green triangle. We're going to give it a letter to identify it. Let's call it green triangle A. All right, so this is green triangle A. Triangle A. Okay, so let's make a triangle that is equal to triangle A. We'll call it triangle B. And it's, we have to be a different color green because, even though we are saying they're the same, we do want to be able to tell them apart. So here's triangle B. All right. Now so Euclid says our common notion is that things which are equal to the same thing are equal to one another. So we need one more thing, just to be careful here. So let's go ahead. Oh no, let's do it this way. Let's go ahead and make triangle C. So I copied, I pasted, and here we go. I'm gonna fill this one with another green. I need more fill colors. Give me another green with a green up here somewhere. All right, let's go over this way. Kind of super yellowy green. Okay, there we go. That's clearly different. All right, and we'll call this one triangle C. There we go. Okay, so we have triangles A, B, and C, and just to make my life feel better so I can feel better about myself, I'm going to go ahead and I'm going to group the letters with their triangles because that's what they are. They work together. They're friends. All right, let's group triangle C. Here we go. All right. So all Euclid is saying here in postulate 1, or in common notion 1, is that things that are equal to the same thing are equal to one another. What that means, of course, is that since triangle... there we go. Is that since triangle A... I should be able to write in here. Do I have a triangle thing? I don't think I have a triangle. So I'm just going to say A is equal... is equal to B. And A is equal to C. Therefore, says Euclid, and this is the big payoff, C is equal to B, because both of them are equal to A. All right? So we know that A and B are equal because we copied B is literally just a copy-paste of A. And we know that A and C are equal because C is just a copy-paste of A. And so what Euclid is saying is that therefore C is equal to B. And we can, of course, test that by doing this. Boom! Boom! Look at that. It fits perfectly on top of B. And we can take it off, and just to double check, we can do it this way. Boom! Boom! B fits perfectly on top of C, which is exciting. There we go. C, so the letter got, there we go. We moved them, but it's still good. All right. So there we go. Things that are equal to each other are equal to one another. We now know that that is the case. So there we go. That is what Euclid is saying with common notion 1. Let's move on to common notion 2. By the way, you're going to notice that most of the common notions, actually 4 out of 5, are basically about equalness and what it means for things to be equal. All right, let's move on to common notion 2. I don't like the period up here. I'm going to take it out. All right, common notion 2, according to Euclid, is if equals B, Abe. B added, did you know that Abe is the last name of the Prime Minister of Japan? Just the more you know. 2 equals the wholes are equal. Okay, this is actually really fun to show. So if equals are added to equals, the wholes are equal. So if you take 2 equal things and you add them to 2 other equal things, the wholes are equal. So let's go ahead and show what he means by that exactly. So here is a thing. And I'm going to do a thing now. Here is another version of it, but it's a little smaller. Okay. Now let's do this. Oh, and then we don't believe in outlines. No outline. No outline. So you can see that they just kind of join right up there. Let's make them different colors just to make this easier. And that's fine. That's a fine color. And that's that one's there. Okay. So again, pretty straightforward. But we have to give our things letters just so that we know what we're talking about. All right, so we'll call this one, rectangle A. Quadrilateral A. We'll call it quadrilateral A because that's the sort of thing that it feels like we should be naming these things. And we'll call this one quadrilateral B. We'll use the terminology that Euclid uses. All right, so quadrilateral A and quadrilateral B. Now they're not equal to each other. Don't worry, that's not my problem so far. I haven't screwed up. Okay, so he says if equals be added to equals, the wholes are equal. Okay, so what let's do here is let's make something that we know is equal to quadrilateral A. We'll call it, here it is, I just hit copy and paste. We'll call it quadrilateral C. All right, oh, and then copy pasted B, call it quadrilateral D. All right, so now we know that, and just to remind ourselves here, just so we don't forget, let's just say that, okay, so obviously now A is not currently equal to B, but A is, I never changed this to C. Right? So we know that A is in fact equal to C, and we know that B is equal to D, because I just did those things. All right. So what else does that mean? Well, what Euclid is saying is that if that's true, then let's separate these for just a second here. I should probably have grouped them, shouldn't I? Let's do that. Group. And just do this as well. Group those. Okay. So move these around together. Okay. So what he's saying is if I add B to A, then I have a new shape. I'll call it shape AB. It's a quadrilateral AB, right? And if I add D to C, right, that's a new quadrilateral. It's a quadrilateral CD. And what Euclid is saying is, since there we go. Since A equals C and B equals D, then if I add B to A, the quadrilateral I get is exactly the same as the quadrilateral I get it equals the quadrilateral I get if I add D to C. So AB is equal to CD in combination. Neat, huh? That's, or if we wanted to put this in careful mathematical terms, we could say A plus B is equal to C plus D. I'll make this a little bigger so that it all fits on line. Right? So there we go. That's all he's saying. So anytime you take two things that are equal and you add them to two other things that are equal to each other, you get two new things, the combos that are equal to the other combos. Okay, let's move on to common notion 3. Common notion 3 for Euclid is if equals be subtracted from equals. I think you might see where he's going here. The remainders are equal. All right. So what we're going to do here, this sort of makes sense, especially if common notion 2 is correct. This seems to be pretty straightforward. But let's go ahead and we'll work it out ourselves as well. It's not going to take long. So I'm just going to take my whole setup from 2, move it down here to 3. And because now what we're going to do is we're going to say if A equals C and if B equals D, all that's true, then A minus B equals C minus D. That is to say, if I take B and I do that, actually this isn't the way, let me put my notation back there. I did not do that notation right. Let's do that properly. Okay, so what he's actually saying is if AB equals CD, so far we agree, then A minus B equals C minus D. Right? So that's what he's actually saying. So if we take B, which equals D, and we take that away, and we take the equal away from, if we take B away from AB and we take D away from CD, then A will equal C. Then A equals C and B equals D. That's it. That's what he's saying in 3. Okay, let's move on now to 4. I told you some of these are pretty easy. Okay, 4. Common notion 4 is an interesting one. He says, and I've actually cheated and I stole from this one because we agree with it. But here we go. Things which coincide with one another are equal to one another. Okay. This one I think is probably more common notion-y than almost anything else we've done. Let's do it though. So to coincide just means like to take up exactly the same amount of space. To take up an exact, not just amount, but the exact same space. So here's a triangle, right? And we'll just call it blue triangle. I'm not going to bother with, I don't know if that's blue or purple, but it's what it is. Blue triangle, and we'll make this one green triangle, right? Oh, we still don't believe in outlines, though. No outline. No outline. Okay. So we got blue triangle and green triangle. If they take up the same space, then they are equal to one another. And look at that. There they are taking up the same space. And being all equal to each other, we can test that by let's send this to back. Send that to back. All right, put the blue one on top of the green one, make them coincide, take up exactly, and look at that. Therefore, we know that they are equal. That is to say, each side of them, to say that triangles are equal, by the way, means each side is the same length, the internal angles are the same as each other, the external angles between them and whatever else you continued with would be the same. All right, so these two are equal if they coincide. So really, the whole critical, the tricky part with 4 is only this term coincide. It means if you can put them right on top, things that are on top of each other equal each other. I don't have my triangles on top of each other here just because I want you to see that there are two triangles. But remember, we have done it. You've watched me do it. Look at that. They actually are equal to one another. Huzzah. Okay. Let's go on to our last common notion. So it said there are only 5 common notions. Last common notion. Euclid says, the whole is greater than the part. This is the only one that doesn't have any equalness in it. The whole is greater than the part. In fact, it's about sort of not being equal. Okay, so for that, I'm going to steal from 2 again. Just going to steal this part, though. Copy. All right. So what's he saying when he says the whole is greater than the part? All he's saying is that... Steal my notation here. All right. So that he says that you've got AB is larger than A or B. Or to put that more, let's put that more technically. AB is larger than A, and AB is larger than B. Right? So AB is a shape made up of A and B, and if we took B away, A is smaller. Right? A is smaller than AB, and if we took B away, if we took A away from it, then B is smaller than AB. That's really all he's saying, and that seems so incredibly obvious. You might be thinking, did I get that? Did I understand it? Nope. He really means that. He just wants us to all understand that a whole, a combination of things, is always larger than those things when not combined. You take a piece away, you have something smaller. The whole is greater than the part. That's it. That's actually all he's saying. Okay. I hope you feel good about the common notions. They're probably the easiest thing to feel good about. So I hope you feel good about the common notions. In our next class, we are going to move on to Euclid's actual proofs. We're going to start proving things. And some of the stuff we're going to prove might actually blow your mind just a little bit. I will say this. Between now and the next lesson, something that would probably be a pretty good idea to do is to go ahead and get a protractor. Get a hold of a protractor. Those are those... Not a protractor. You don't need a protractor. You can do all this without a protractor. A compass. A compass is one of those. It's two arms to it with a pencil usually attaches to one arm and a little spike on the other arm, and you use it to draw circles. You don't have to, because I'm going to try to do all this in the video and on PowerPoint. But you might find it very, very useful to get a hold of a protractor. And a straight edge, right? So a ruler, basically, a ruler, and maybe come to the next one with a piece of paper. Because while I'm going to work through the first proof, I think it might be fun for you to kind of do it yourself while you're watching me, or like right afterwards, just to see for yourself. Because actually, what it shows you how to do is pretty neat, in my opinion. Okay, that is it for today, and I hope you enjoyed it.